Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video. By the end of it, you should be able to use calculus to solve optimization problems. So optimization is just calculating the maximum or minimum value of things. So let's look at this example here. Rocket is launched from ground level. Its height above ground level is given by this function here. Y is the height in meters above the ground. X the number of seconds after the rocket is launched. And we're going to calculate the maximum height reached by the rocket. So this is a pretty easy example, and I say that because we've already looked at solving problems like this before. When we did this previously, we just used parabolas and found the turning point of a parabola. This time we're going to use calculus. So there are a lot of words in this question, but essentially all it's asking us to do is calculate the maximum of this function here. So I'm going to quickly draw a rough sketch of this function here. You don't need to do that when you're solving this problem, however. So this is what the function y equals 32x minus 2x squared looks like. But this isn't actually the path of the rocket. See, the rocket isn't moving along in space like this. The rocket is actually moving in a straight line. It's actually going straight up, and then it stops, turns around, and comes back down. The path of the rocket is a straight line, not a parabola. This is just a function that tells us what the height of the rocket is above ground at a given time. Each of these values here, along these x values, is a time value, and the y is how high it is. Is it up here or is it down here? But the rocket is traveling in a straight line. So now that we have that out of the way, we're just going to calculate the maximum value of this function, which is really easy. So firstly, we're going to calculate the derivative. So that's just going to be 32 minus 4x. So we want to know when this derivative equals 0 to find the stationary point, to find the maximum point, which is here. So solving 32 minus 4x equals 0, I just get x equals 8. So that means that the maximum height occurred after 8 seconds. So if x equals 8, y equals 32 times 8 minus 2 times 8 squared, giving me 128 meters. That is the maximum height reached by the rocket. Now, unlike in the previous video, I don't need to check the endpoints of the interval or anything like that. I know that this is going to be a global maximum because that's how parabolas work. They always have a global maximum or a global minimum. So I'm done here. Maximum height 128 meters. Let's look at a slightly harder question. So let's try this question here. Squares are to be cut from the corners of a 15 centimeter by 20 centimeter rectangle to make a 3D box, and we're going to calculate the maximum value of this box. So let's start by drawing our rectangle here. So what we're saying, there's going to be squares cut out from the corners like this. And then what I'm going to do is I'm going to fold up this edge here, and make it into a box. So I was told that the rectangle is 20 centimeter by 15 centimeters, and let's call the length of these squares here x. So we're going to find out what would be the maximum volume when I turn this into a 3D box. So the volume of a rectangular prism, the volume of a box, is just the area of the base times the height. So this is going to be the base of the box here in green. So its dimensions will be 20 minus 2x by 15 minus 2x. And this length here, which is x, that will be the height of the box. So the volume of the box is just going to be height of the box times the area of the base, so width times length. So all we need to do now, we've done the hard work, we just need to find the values of x for which this function here is a maximum. So we're just going to start by expanding the brackets. So if you don't remember, you use FOIL to expand these brackets. 15 times 20, 15 times minus 2x times 20, minus 2x times minus 2x. So this is what I get after using FOIL and timesing everything by x, I get this. So I want to find the values of x that make this function here a maximum or minimum. So to do that, I'm going to differentiate it. So I would get 300 minus 140x plus 12x squared. So I now want to find the values of x that make this function in red equal to 0. So this is just a quadratic, so I can use the quadratic formula. So firstly, I calculate the discriminant, b squared minus 4ac, which gives me 5200. So that means x will be minus b plus or minus the square root of the discriminant over 2 times a. So putting that into our calculator, we get the two solutions about 8.84 and 2.83. So it's a little more complicated here because our original function was a cubic. So in the previous example, when we were using a parabola, that's really easy. It has one stationary point. We knew it was going to be a maximum and a global maximum at that. Here we have two stationary points. We don't know whether they're local minima or local maxima. So to do that, we need to utilize our first derivative test. So remember, to do the first derivative test, I set up a table, so I have both of my stationary points here, and for each stationary point, I need a value either side of it to check the gradient function. So if I substitute x equals 2 into this function here, I get positive 68. I know if I substitute x is 2.83 into the gradient function, I get 0. Same as if I substitute 8.84, I'd get 0. If I substitute x equals 4 into this gradient function, I get minus 68. And if I substitute x equals 10 into this function, I get another positive. So what that means is my function v here, what it's doing, that means it's going to be increasing at x equals 2, then at 0, then decreasing at x equals 4, 0 again, increasing at x equals 10. So I've just found out that at x equals 2.83, that's a maximum turning point, and at x equals 8.84 is a minimum turning point. So this question only asks the maximum volume. So I'm only interested in the maximum turning point. So the maximum volume is going to occur when I substitute x equals 2.83 into this function here. So if I substitute x is 2.83 into this original function here for the volume, I get that the maximum volume is approximately 379, and of course it will be centimeters cubed because the measurements in the question were given in centimeters. In this question, I don't need to check the endpoints. It turns out x would had to have been between 0 and 7.5. So it couldn't be any more than 7.5 because then this dimension would be negative. But the volume of the box would be 0 at these 2 points. So I can be confident there's no other value of x that could possibly give me a larger volume than this. Alright, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.